In the middle of the day, the sky starts to darken. It's as if dusk has fallen early. People look and notice something is happening to the sun. A dark shadow moves before it, gradually devouring every last trace of brightness until our familiar light bringer is only a shimmering, ghostly ring around a pitch black orb. A total eclipse is occurring. This will soon be a reality. One is coming to the continent of North America in April 2024. But if, like me, you are one of the many billions of people who won't get a chance to see that particular solar eclipse this April, you might be glad to know that America is not the only place they happen. And neither is Earth. Have you ever wondered what a solar eclipse looks like on another planet? Wonder no more. I'm Alex McColgan and you're watching Astrum, and today we're exploring solar eclipses, but not just the ones that happen here on this planet. Allow yourself today to feast your eyes on the actual images and even videos NASA has taken of spectacular eclipses from various places around the solar system. Firstly, I'll quickly explain some of the terminology to do with eclipses. A total solar eclipse is when an object moves in front of the sun, completely obscuring it, also known as an occultation of an object. This is the typical kind of eclipse we see on Earth when, at certain points in Earth's orbit, the orbit of the moon aligns with the sun. There is something special about an eclipse here on Earth, and I'm not just saying that out of some Earth-focused pride. By a bizarre but highly fortunate cosmic coincidence, the moon is the right size and distance from us that its angular diameter is almost identical in size and shape to the angular diameter of the sun in our sky. This leaves for an impressive spectacle where the corona of the sun, or in other words, the sun's upper atmosphere, creates a ghostly aura around the moon. This corona, normally too dim to see, extends for hundreds of thousands of kilometers into space. Looking closely around the edge of a total solar eclipse, and you will also see the silhouette of the moon's craters along the outside, plus these reddish wisps coming off from the sun. These are prominences, millions of tons of charged particles suspended in the sun's atmosphere by powerful magnetic fields. During an eclipse here on Earth, the moon casts a shadow about 250 kilometers in diameter, which moves across the Earth as the moon orbits. In the case of the eclipse happening this April, this shadow will arrive at the Mexican west coastline, then will make its way up through the United States until it passes into parts of Canada before moving over the ocean once more. You can see on this map the path the shadow will take. If any of you happen to live in its pathway or are close enough to make the drive, you may want to try and see this eclipse for yourself. The sun will only be totally obscured within the diameter of this shadow. Outside of that, the sun is only partially obscured from the viewer's perspective. This viewer is witnessing an annular or partial eclipse, also known as a transit. The shadow moves across the Earth extremely fast, at roughly 1 kilometer a second. Witnessed from a high altitude, it is a majestic sight as the shadow shifts across the landscape. Satellites have also witnessed the movement of this shadow. The shadow isn't as sharp as you might expect, and this is due to the angular diameter of the sun and the moon and their distance apart. The sun itself is huge, a whopping 1.4 million kilometers across. The moon is much smaller, at only 3,400 kilometers across. Now, this image isn't to scale, but it shows visually why the shadow isn't sharp. The umbra is the shadow where the sun is completely obscured, and the penumbra is the shadow where the moon only partially obscures it. This part of the shadow is much wider than the 250 kilometer wide umbra shadow. So why doesn't the moon create eclipses every month when it orbits in front of the sun? Well, this is because the moon's orbit is not in line with the Earth's orbit around the sun. This means there are only a couple of times per year when the alignment is right. This alignment of 3 celestial objects is known as a syzygy. A very cool word, but not something you'll need to remember for this video. I just thought you would find that interesting. If you live in the UK like me, sadly you won't get to see much of the eclipse this April unless you live at the furthest west parts of the country, as the sun will be dipping below the horizon just as it begins. Maybe we will get to see some devil's horns though. Still a spectacular sight indeed. But the Earth is not the only place to experience solar eclipses, and we have the images and videos to prove it. Let's explore eclipses of our closest celestial neighbor, the Moon, because it would make sense that if the Moon can occult the Earth, then surely the Earth can occult the Moon. And the answer is yes. But it's not the shadow that's the really visually appealing part of this, from the Earth anyway. This is because the Earth is 4 times as big in the Moon's sky as the Moon is on Earth's, so when the Earth fully obscures the Sun, the whole Moon is in the umbra. At first, the shadow of the Earth creates a crescent shape. Explain that, flat earthers. But what is different this way around is that, unlike the Moon, the Earth has an atmosphere. This means that when the Moon is totally eclipsed, the Earth's atmosphere refracts the Sun's light around the planet, gently illuminating the Moon in a reddish hue. This makes for a beautiful but almost spooky view. The color is caused by Rayleigh scattering, a topic I've discussed in another video. Rayleigh scattering is the same process that makes our sky blue and our sunsets red. This image is beautiful in that you can see the different wavelengths of light being scattered through Earth's atmosphere, from deep red from this side through to blue on this side. From the Moon's perspective, none of the Sun would be visible during a total eclipse, but the atmosphere on Earth would be illuminated, so you would see a ring around it. This is an actual view of a lunar eclipse on the Moon by one of the JAXA probes in 2009. It's quite the awe-inspiring sight. The Earth and Moon aren't just getting in the way of each other either. Here is the Earth eclipsing the Apollo 12 spacecraft in 1969 while it was on its way back home. And here's the Moon getting in the way of the Earth from the perspective of the Discover satellite. Interestingly, this is the side of the Moon you never see, as the Moon is tidally locked to the Earth, which means the same face is always looking towards Earth. From this perspective, the Moon looks very foreign. But it is indeed a real video of our only natural satellite transiting the Earth. From another satellite's perspective, but this time looking at the Sun with the SDO satellite, the Moon often makes an appearance. The position of this satellite as it orbits the Earth means the Moon can block the Sun occasionally. And here's the Moon again, this time from the perspective of one of the stereo satellites. The Moon isn't the only thing that orbits between us and the Sun. Mercury often transits across the Sun, a tiny minnow compared to the solar system's giant. The next time this will happen is on the 13th of November 2032, so a little while away. You might want to put it in your calendars for now. Venus also orbits between us and the Sun, and as it is much closer to us and bigger than Mercury, its silhouette appears much larger. Its last transit was in 2004 and 2012, but sadly if you missed those two, chances are that you will never see it. These transits happen in pairs, and then there is a 100-year gap until the next one. In other words, the next transit will be in 2117. This happens for the same reason the Moon doesn't eclipse us every month. The orbits just don't often align. Still, we have high-definition videos of the last one, and it is quite the sight to behold. Moving to another planet now, we can go to Mars, which has plenty of unmanned robotics either in orbit or on the surface. Mars also has 2 moons, Phobos and Deimos. They are both pretty small. Phobos is 22 kilometers across, and Deimos is only 13 kilometers across. They both orbit very close to the planet though. Phobos is only 9,000 kilometers above the surface, and Deimos is 23,000 kilometers, which means, although tiny, you can still easily see them from the surface of Mars, especially Phobos. The Curiosity rover was able to capture a moment where, incredibly, Phobos eclipsed Deimos. This video is captured in real time and shows the size differences of the moons in the Martian sky. And this is not all the Curiosity rover captured. It was also able to see a transit of Phobos in front of the Sun. Due to the distance of Phobos to Mars, it moves across the sky fairly quickly, only taking about 7 hours to orbit once. This means that this video you are watching is in real time, and these solar eclipses on Mars don't last for more than about 30 seconds. The surrounding ground does get noticeably darker during an eclipse by Phobos, as can be seen from the rover's perspective, but it can also be seen from space. Phobos' shadow here can be seen by the Viking 1 orbiter, and also here more recently by the Mars Global Surveyor. The Opportunity and Spirit rovers have also seen a transit of Deimos, but it appears much smaller, just a dot passing in front of the Sun. It doesn't cause a noticeable decrease in brightness. Mars is pretty impressive, but that's not all the solar system has to offer. Have a look at this video captured by the Hubble Space Telescope, looking at Jupiter. Jupiter has 4 large moons, 3 of which at certain points can transit the planet at the same time, leaving 3 big shadows. The moons in question in this video are Io, Callisto, and Europa. Interestingly, like we talked about before with the Umbra and Penumbra, you can see that because Io is the closest to the planet, its shadow is the sharpest. Whereas you can see with Callisto, the furthest away of these 3 moons, the Penumbra is much larger, causing a blurry shadow. And in this video, Hubble spies the occultation of Ganymede, the largest moon of Jupiter. Cassini saw some incredible transits and occultations of Saturn's many moons. Here is one of Epimetheus passing in front of Titan, with Dione coming in from the side. This little white dot coming in from the left just under the ring is in fact a bright background star. And this Hubble view is magnificent. Here are Enceladus, Mimas, Dione, and Tethys orbiting Saturn. Once every 15 years, Saturn's rings and moons are aligned just right so that the moon's shadows stream across the rings as well as on the planet. This video is a time-lapse that lasted 9.5 hours. Amazing. Going a bit further out, we come to Neptune and its biggest moon, Triton. Sadly, we don't have a video, but this image captured by Voyager 2 is gorgeous. 3 days after passing by Neptune, Voyager was able to capture the crescents of Neptune and Triton before Neptune slipped in front of Voyager's view of Triton. Going further out again, we come to the furthest celestial object explored in the solar system, Pluto. As New Horizons whizzed by Pluto in 2015, it turned its camera back towards Pluto to capture the dwarf planet totally eclipsing the Sun. What it saw was dazzling. The sunlight streaming through and illuminating the atmosphere and its haze layers, with the ridges and mountains on Pluto's surface highlighted by the stark contrast of Pluto's night side. Occultations and transits may be breathtakingly beautiful, but are they actually useful to us scientifically? Well, did you know that Uranus was discovered to have rings because of an occultation of a background star? As the planet passed in front of the star from our perspective, the star dimmed before and after the planet obscured it. With this information, we are able to count how many rings Uranus has. On top of that, the transits of exoplanets in front of their stars are actually how we can detect exoplanets. Telescopes like Kepler and TESS measure the brightness of stars in the sky. If a star dims, it could be because one of its planets just passed in front of it. If the star continually dims in a pattern, for instance once every 100 days, then we know that a planet orbits that star and takes 100 days to do so. Using this method, space agencies like NASA have discovered over 3,000 exoplanets, more than all other methods of exoplanet detection combined. It can even help scientists calculate the size of the planet by measuring how much the star dimmed, or the composition of that planet's atmosphere by looking at the spectra of the light that passes through from the star to us. It might be some time before we see a solar eclipse again. After the one in April, the next eclipse won't happen in America until 2044. Here in the UK, the next one won't occur until 2090. If I live to see it, I will be a very old man. But I'm amazed as I see all of the images of eclipses that take place throughout the solar system. There's a special beauty to each one of them, a fleeting moment where one celestial body brushes lightly against another, even if it's only through their shadows. Rather than harbingers of doom, these moments fill me with awe and remind me how connected the universe is. Even across thousands, millions, or even billions of kilometers of space, we can notice a planet's passing. And if you're in the right place at the right time, oh, what wonders you can see. You may have heard many news stories about all the thousands of exoplanets that have been discovered using the Kepler telescope. As of the 1st of July 2018, Kepler has confirmed the existence of 3,797 planets in 2,841 star systems, with 632 systems having more than one planet. But are any of these planets habitable? What are the chances of life being found outside of Earth? Are we alone in this universe, or can life be more prevalent than we think? And if there is life, where can it be found? I'm McColgan and you're watching Astrum, and together we will explore known exoplanets in the Milky Way galaxy to see if any of them have the potential to harbour life. Now, we've not been able to actually image exoplanets in any kind of detail. In fact, this is the clearest real image we have of an exoplanet, taken by ESO's Very Large Telescope, which may make you question, if this is the best image of an exoplanet we have, how can we discover exoplanets, and how do we know life could be on one? To answer the first question, we have to look at how Kepler worked. Kepler is a space probe which constantly monitored about 150,000 stars in a fixed field of view using its camera. The field of view focuses on a patch of sky near the constellation Cygnus. This is what Kepler can see. The data it collects is sent to Earth and analysed to see if any stars dim periodically. You see, the concept is, if a star's planet passes in front of Kepler's view, the star will dim. If it dims, for instance once every 100 days, we can confirm that it is a planet and it takes 100 days to orbit. Kepler is really good at finding exoplanets. Before Kepler came into operation, these were the exoplanets we knew about. As you can see, most of them are many times the size of Jupiter. Since Kepler came into operation, we have discovered and confirmed the existence of thousands of exoplanets, with thousands more still unconfirmed. Remember, these are planets which have been discovered in only this patch of sky. There is still a lot more out there. Kepler unfortunately is no longer functioning how it used to, as some of the reaction wheels inside it are broken. However, the good news is that there is a new exoplanet finding spacecraft called TESS, which just came into operation a couple of weeks ago, which will cover an area in the sky 400 times larger than the Kepler mission. It is expected that during its mission it will be able to find more than 20,000 exoplanets. In order to determine details about an exoplanet, the distance from us to its star needs to be worked out using complicated maths. For stars within 400 light years away from us, we can use trigonometry and the orbit of the Earth to create a difference in angles. Beyond that, there is no direct measurement, so the best current method is by comparing a star's color spectrum to its brightness. The color spectrum of a star corresponds to what type of star it is. Once the color spectrum is known, scientists then know how bright the star should be. Comparing the apparent brightness, or the apparent magnitude, to the actual brightness, the absolute magnitude of the star, reveals how far away it is. This method is proven, as scientists have done this test on stars that are within 400 light years, and the results produce similar distances in both tests. Once the distance to the star has been determined, the amount the star dims can be used to see how big the planet is, its distance from the star, and the exoplanet's mass based on the orbit of the exoplanet. Using other telescopes like Hubble, ESO, and eventually the James Webb and the WFIRST telescopes, these exoplanets can be studied to find out their composition, particularly of their atmospheres. The way this is done is again from the spectra of the exoplanet's light. To give you an example of how this is done, imagine white light shooting through a prism, producing what is actually a blend of colours spanning from violet to red. Light from a star shooting through an atmosphere produces a similar effect, except certain bands of light are not present. This indicates there is a certain gas in the atmosphere that is absorbing the light in that wavelength, not allowing it to pass through. The dips in this image shows what Earth's spectrum looks like as sunlight passes through the atmosphere. The dips show that oxygen is present, as well as water vapor, carbon dioxide and methane. These gases all absorb the sun's light at these wavelengths. Looking at the section of wavelengths and comparing them with other planets in the solar system, sulfur compounds can clearly be seen on Venus, and methane on Neptune is apparent. This means that as we study exoplanets in detail and determine their spectra, we can search for atmospheres that resemble our own. If it does, then the chances are that it could be a habitable world, and also that it may already harbour life. Inhabited planets could have telltale signs of life, like smog and pollution, which would be seen in the planet's spectrum. So, have any exoplanets like these been found? Well, out of the thousands of exoplanets that have been discovered, 16 of them are thought to be rocky planets and sit in the Goldilocks zone, or the habitable zone of their respective stars. Let's just remind ourselves of the ingredients needed for life as we know it. We believe that liquid water needs to be present. Liquid water is essential because biochemical reactions can take place in water. Water is also an excellent solvent that easily dissolves and carries nutrients and other compounds in and out of cells. Life forms on Earth are made primarily of water. In fact, our human bodies are more than 60% water. Life also needs sufficient protection from cosmic and solar radiation, which can break down and damage cells. On Earth, this protection comes from our magnetic field. There also needs to be essential chemicals found in the ground on Earth, and an energy source, which for us is the sun. So the Goldilocks zone is where, assuming other conditions are right, liquid water could theoretically pool on the surface. This zone is always different depending on the parent star and how big and hot it is. Looking at our own solar system, Venus might just be in the Goldilocks zone, as well as Earth and Mars. We already know that only 1 in 3 planets in our own solar system's Goldilocks zone can have liquid water, so just being in the right place is not always enough. The type of star is also important. Our star, although seemingly active on the surface, is actually quite stable compared to a lot of other types of stars. The Sun will likely be 10 billion years old before it burns out. On the other hand, the hottest types of stars will only last for millions of years in comparison. It is thought that this is not enough time for life to form around it, certainly not animal life that can communicate as we understand it. So we have a lot of filters we can now use to narrow down our search for habitable worlds. Out of the original 3,797 confirmed planets, 16 are terrestrial planets that orbit within the Goldilocks zone of their stars. However, the habitable zone of some stars means the planets are close enough to be tidally locked, meaning only one face of the planet sees its star. This proximity to the star also means the planet is exposed to a lot of solar radiation, sometimes thousands of times more than we are exposed to on Earth. In other words, out of those 16, only 4 are likely candidates to be Earth-like, although it is worth mentioning that exoplanets in systems like the TRAPPIST-1 system could still be habitable or have life even if all the planets are tidally locked. But the TRAPPIST system is worthy of its own video, so I won't expand on it here. These 4 exoplanets are Lytton B, Kepler-62f, Kepler-186f, and Kepler-442b. Realistically speaking though, we don't know much about them other than their size and mass. Our current technology isn't accurate enough to determine the composition of their atmospheres. One of the James Webb Space Telescope's missions is to study known exoplanets in greater detail, which is exciting as, in combination with the finding power of the TESS telescope I mentioned earlier, this next decade could be full of discoveries. But by using the Kepler data as a fairly decent sample size, can we estimate how many habitable worlds there could be in our galaxy alone? Ethan Siegel did a very interesting article, which I will link to in the description, where out of those 150,000 stars, the chances of seeing anything at all using the transit method is very small, less than 1% for a planet orbiting the distance of Mercury, let alone Neptune, which has a 0.001% chance of detection. This is due to the way planets tend to all orbit along a plane, and if it's not lined up, we won't see anything. Also, smaller planets are much harder to detect. Look how hard it is to see an Earth-sized planet compared to a Jupiter-sized planet. Taking all these things into account, Ethan Siegel placed a low estimate of 6.4 billion planets in their star's habitable zone in our galaxy, the Milky Way. This means at least one of them has to have life too, surely. Well, we really don't know how prevalent life is at all. And until we do some serious research and improve our technology, we have no way of knowing yet. Some people claim that all factors considered, the chances of humans being able to develop and live on Earth was 10 to the power of 10,123 to 1. In other words, extremely unlikely. How many factors actually are needed to be right for life to exist? Is it all over the place, or purely a freak coincidence here? Building on what we know already means the future is going to be very exciting.
For almost all of human history, the night sky has guided us across continents, illuminating our path forward. The stars are as entwined with our civilization as are the land and the sea. But that sky is changing. While the stars, nebula, and supernova remnants are as brilliant as ever, few of us will ever get the chance to see them as they once were, even though all it would take to do so is a flick of a switch. I'm Alex McColgan and you're watching Astrum. Join me today as we explore how the night sky has changed in our own lifetimes and uncover the drastic effects that artificial light, both visible and invisible, has had on us, on crucial ecosystems, and on important scientific research. We will see how a well-intentioned green revolution made it worse, how we've put artificial constellations of our own into orbit, and how even the natural constellations themselves are changing. That's right, we're going to see how our sky will change in 1,000, 1 million, and even billions of years into the future. As it is with anything that changes gradually over time, we rarely realize what is happening. But every once in a while, that gradual change can be laid bare, as it was during the 1994 earthquake in Los Angeles. A large part of the city's electrical grid was knocked out in the early hours of January 17th, revealing the effects of decades of increased light pollution in an instant. So shocked were the residents by what they saw as they evacuated their homes that some looked up in awe of what had always been there, hidden by the city lights. One even phoned the observatory to ask what the giant silvery cloud was that they were seeing. Sadly, even the sky when you first looked at the stars as a child is not how it is now. From 2011 to 2022, the average light pollution increased by 10% a year, meaning it has more than doubled over that time. So let's travel to a dark sky location on a clear night, far away from the sky glow of towns and cities, and look up to understand what we've lost before we learn how we might get it back. There is a useful measure used to rate the quality of the night sky by eye called the Bortle scale, which ranges from 1 to 9. In a city under the brightest of skies, you may only be able to count 100 stars. This is a 9 on the Bortle scale. But as you travel away from the lights, the sky reveals more until it becomes nearly unrecognizable. As you drive out to the surrounding urban area, the night sky darkens to Bortle 7. Here on a clear night you might get to see a hint of the Orion Nebula, visible only as a diffuse looking star. Clouds under these skies will be very well lit. Once you're out past the city limits into the rural countryside, you're now under Bortle 3 skies, and much more is revealed. Messier objects 15, 4, 5 and 22, all star clusters, are now naked eye objects. Andromeda is clearly visible, and if you look carefully, you'll glimpse the Triangulum galaxy. These two galaxies at 2.5 to 2.7 million light years away are the furthest objects we can see with the naked eye. And what about that giant silvery cloud they saw in Los Angeles? That's our Milky Way, a diffuse band that arcs across the sky, which contains over 100 billion stars. Finally, after a few hours of driving, you're now under Bortle 1 skies, a true dark sky sight with a pristine view. When we set out from the city, you could only see 100 stars. Here, you will see thousands. It may even take you some time to notice the constellations that you thought you knew, lost as they are in the awesome detail of this dark sky. If you're lucky enough to live in the southern hemisphere, you'll be looking towards the galactic center, and you may even notice that it casts shadows onto the ground. My friends in the northern hemisphere, no need to be envious. Our fortunes will be reversed as we orbit to the opposite side of the galaxy in a mere 120 million years. Elements of the beautiful Orion complex are visible in both hemispheres, a 1,200 light-year wide star-forming region containing the Horsehead, Flame, and Orion nebulae, though binoculars are strongly advised. The closest object that is fully revealed in such a dark sky produces no light of its own: interplanetary dust. This dust is illuminated by the sun and forms a band known as the zodiacal light, which spans from the horizon to horizon, featuring a central focus called the Gegenschein, appearing directly opposite the sun's position over Virgo. Sadly, those of us who live in cities never experience a genuine night sky at all, and are effectively stuck in an artificial twilight. This can have unexpected effects on us as well as the night sky. So how do a few light bulbs block out an entire galaxy? In a word, sky glow. Any light that is emitted upwards will pass through the atmosphere where it can be scattered in any direction. The light that is reflected back towards the ground to our eyes or telescopes is seen as sky glow, which has the effect of drastically reducing the signal-to-noise ratio of incoming light from space, affecting our ability to see it and to study it. You may have experienced something similar on a dark, foggy drive. Perhaps in an attempt to see more of the road, you've turned on your full beams. The slight upward angle of these lights reflects light up, illuminating the fog in front of you, which has the opposite effect of what you intended. It bleaches the field of view and obscures the road ahead. To make things worse, it's not just that the sky is now brighter. Tragically, our eyes are now also less able to see in the dark when we go outside. Human eyes have the incredible natural ability to detect brightness across a full 9 orders of magnitude. We are able to do this because we have 2 types of vision. The first is known as photopic vision, and it's the one you're using now. It's our daytime color vision recorded by our eye's cone cells. The second is scotopic vision, an ultra-sensitive monochrome night vision recorded by our eye's rod cells. It is this scotopic vision that allows us to see the faintest details in the night sky. Modern lighting is reducing our access to scotopic vision because, to the human eye, all light is not equal. In the past 10 to 15 years, a movement towards more energy-efficient LED lights has shifted the spectrum of light pollution from the orange hues of the sodium lamps to the blue-green frequencies of LEDs, which we are much more sensitive to. These blue-green frequencies slow down dark adaptation, or worse, can fully reverse it in minutes, which is why you'll often see astronomers and nighttime pilots using red lights or red goggles to ensure scotopic vision is maintained. To access full scotopic vision, we require a near absence of short frequency light for at least 30 minutes, and it can continue to improve for up to 2 hours. So, you may be wondering, if we are so sensitive to the blue frequencies of typical LED lights, why can't we use less of it and reduce overall light pollution? And you'd be right, we could. The reality is, though, that we don't. LEDs are so efficient compared to sodium and filament lights that we save energy and money even when they're run much brighter. So that's what we often do. We run them brighter because we all feel safer in a well-lit area, even if we are statistically no more likely to be the victim of crime. Our eyes also contain retinal cells that are not involved with seeing and instead help to regulate our body clock. These cells are particularly sensitive to shorter wavelengths too. So, artificial light, and LEDs in particular, don't just affect our ability to see the night sky, they affect us in other, more severe ways too. The disruption of our circadian rhythms by light disrupts the production of several key hormones, including melatonin. Incredibly, this can affect our body through a dramatic cascade that can lead to metabolic and mood disorders, and most severely, cancer. While for us humans there is at least some upside in extending the length of the day artificially, for the rest of nature there is almost nothing but downside. Lights interfere with the circadian rhythms of wildlife too, disrupting how and when they sleep, migrate, reproduce, hunt, and evolve. Almost every species studied to date is negatively affected by lighting, at the level of both the individual animals and their populations. Scientists have studied fishes, birds, amphibians, insects, invertebrates, ecosystems hundreds of meters down below the surface of the sea, and even trees. Deciduous trees, which regrow their leaves each year, can be tricked into maintaining their foliage all year round, causing stress that can eventually kill the tree. There are simple things we can do that manage that rare combination of saving us money and improving our health. The best, of course, is to turn off unwanted lights, particularly outdoor lighting and uplighting. When installing new or replacing new lights, look to install low power LEDs with low color temperature of say 3000 Kelvin instead of 5000 Kelvin. Well-designed lighting will have shielding to focus the light to where it needs to be and minimize excess light shone into the atmosphere. But away from ground-based artificial lights, we are now facing a significant increase of light pollution coming to us from space. Since 2018, SpaceX has launched nearly 7,000 satellites into space. Oh, and one Tesla Roadster. As it stands, SpaceX have twice as many active satellites in low Earth orbit as every other company and country on the Earth combined. I've seen some hockey stick shaped graphs in my time, but this one is stratospheric. The vast majority of these new satellites have gone into low Earth orbit at an altitude of only 550 kilometers. The United Nations Office for Outer Space Affairs have speculated that 100,000 more satellites could be launched in the next decade. There are no regulations that limit the number of satellites that can be launched, and many agreements and understandings around reducing the potential for light pollution are informal. These satellites in low Earth orbit are particularly bad for light pollution, contributing to sky glow and producing trails in amateur photography and research images that can render them unusable. Astrophotography can require long exposures of several minutes, and it's likely that these exposures will capture the trails of satellites in that time. This is an image of the Horsehead Nebula, and there are 3 trails in this image. And even I myself have seen it in my own shot of the Orion Nebula. We can easily see the effect satellites have on visual astronomy. We can even watch them trail across the sky in real time. But these man-made constellations that deliver GPS, mobile communications, and satellite internet all operate in the radio spectrum too, spanning megahertz and gigahertz frequencies, which can potentially interfere with scientific observations. Radio signals easily pass through galaxies, solar systems, interstellar gas clouds, and Earth's atmosphere, revealing secrets of our universe that would otherwise be hidden. All the more incredible then that the radio signals from my Wi-Fi router can barely make it through a few stud walls. But radio astronomy was key in establishing the shape and rotation of the Milky Way, discovering quasars and pulsars, and detecting organic molecular species like cyanide, ammonia, water, and amino acids in interstellar molecular gas clouds. It was a radio telescope in Ohio that received the famous WOW signal in 1977. It was detected at 1420 MHz, a value believed to be the frequency of choice that an alien civilization would attempt to communicate over, and it is protected from commercial use to keep it quiet. It is though still debated whether the WOW signal was terrestrial interference or an extraterrestrial phenomenon. But while we are talking about how communications interfere with astronomy, astronomy can also interfere with communications. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for discovering that the interference in their antenna wasn't pigeons, it was the cosmic microwave background, the cooled remnants of the universe's first light. The detection of this low-level hum in their Bell Labs antenna and understanding its cause all but proved the Big Bang hypothesis. In another happy accident, the radio waves emitted by the black hole at the center of our galaxy, Sagittarius A star, were detected because of its interference with transoceanic phone calls. I love these 2 stories as it highlights humanity at its best, at its most inventive, and at its most curious. Pausing in the hustle of developing new technologies to remark, that's odd, led to 2 incredible discoveries. So much has been discovered in the radio wave spectrum, yet there are deeper mysteries that cannot go unsolved. That's why the Square Kilometre Array Observatory is being built in radio quiet zones, the most ambitious radio observatory project of all time. I don't say that lightly, it is. Its stated aims are to probe the cosmic dawn and the emergence of the first stars and galaxies, to challenge Einstein's general theory by indirectly observing gravitational waves to seek the origin of life, to look for aliens, and to understand how our galaxy and universe are changing due to pressures like entropy, gravity, and dark energy. But what does that change look like to us from Earth? If we look up to the stars through a polluted sky, space appears stagnant, and it can be easier to believe that we are instead on a Truman Show-like film set with fixed stage lights for stars than on a rock in motion through our galaxy. But under a dark sky, nothing feels still as we get a sense of our voyage through space and time. Earth is orbiting the black hole at the center of our galaxy at 828,000 kilometers per hour. We are heading away from the galactic plane and hurtling in towards the center. Our perspective and every object we can see is moving. In this video by ESA, from data captured by the Gaia telescope, we can see how our night sky really is changing. In 1,000 years' time, only the keenest astronomers would notice a difference from today's constellations, though we may be lucky enough to witness Betelgeuse going supernova. But in around 10,000 years, we will have a new North Star. Polaris will have moved away from the celestial pole, and it will have been replaced by the brighter Vega. And let's take a closer look at the constellation of Orion and the stars around it. They will change dramatically over the next 450,000 years. Orion's sword will shatter and his bow will disintegrate. Zooming out to the entire night sky, let's watch our galaxy evolve over 4.5 million years. Orion is in the bottom right. What we can't know with this data though are how many more stars will go supernova and how many more will be born. We'll just have to wait and see. And that's going to be a heck of a lot easier if you would just turn off those up lights. But over the next few billion years, the sky will begin to look so unrecognizable that you would be forgiven for thinking we were in a different galaxy altogether. Because we would be. Andromeda currently takes up 3 degrees of our sky, about 6 moon widths. It is accelerating towards us and is expected to reach us in 5 billion years, by which point it will be the sky. Galaxies are so diffuse that Andromeda and the Milky Way would pass through each other almost without impact. But it's what we can't see that is all around us that will seal our fate. Gravity. Over the next 5 to 10 billion years, our 2 galaxies will yo-yo and rip each other apart with a huge burst of star formation from the mixing gases, turning 2 spiral galaxies into one elliptical blob. Unfortunately, you would be unlikely to see this from Earth because of the extreme natural light pollution caused by the sky literally being on fire. Our sun will have become a red giant. In 1 trillion years, the last star will be born. There is nothing but decay left for the universe. The galaxies we can see outside of our extended galaxy will become faint and dim as they move beyond our observable universe. In 120 trillion years, all stars will be extinguished and the night sky will fade to black. As is so often the case in our complex world, there are unexpected outcomes from our behaviors. Our night sky is changing in many ways. It has been obscured, but it is not lost. Towns, cities, and governments all over the world are beginning to understand the issues and are making changes in ordinances and in law to protect our skies and the wildlife underneath it. So, if this video has inspired you to visit a dark sky or reduce your impact, head to darksky.org to find out more, and to lightpollutionmap.info if you're curious about the light pollution in your area.
On this world of ours, we take a lot of celestial things for granted. For example, the fact that when there are no clouds in the sky is blue. We have the moon and the sun, which are both about the size of a pea when held at arm's length.
These things are all very predictable, but what if you were standing on a different planet, or even a different moon? How would the sky appear then?
Let's start at the beginning. This is Mercury, the closest planet to the Sun. With no atmosphere and no moon, at night you'd see the whole Milky Way in pristine detail. Venus, the Earth, and even our moon would also be very bright in the sky. During the day, on the other hand, the Sun is the centerpiece of the sky. It can sometimes appear over 3.2 times bigger in the sky than on Earth, and over 10 times brighter. Mercury is in fact very dark grey, but because of the brightness of the Sun, it appears to us like it's white. What about Mars? How does it compare to us? Well, we have a planet that from the surface appears relatively Earth-like. There is an atmosphere, and the Sun appears about 5/8 the size on Earth, which produces the equivalent brightness of a slightly cloudy afternoon here. During the day, the sky is orange to scarlet in colour, and sunsets and sunrises produce these blues and purples. It's quite the opposite of Earth. And during the night, stars are visible in the sky, as well as both of Mars's moons, which appear quite small. Moving on to the outer solar system now, things are going to get even more spectacular. Now, these planets don't have solid surfaces to land on, which means we're going to look from their moon's perspectives. And starting with Jupiter, we're going to land on the surface of its closest big moon, Io. None of Jupiter's moons have anything more than traces of an atmosphere, so the sky of Io itself would appear quite black. The dominant feature of the sky would of course be Jupiter, which would appear a massive 38 times bigger in Io's sky than our moon in our sky. It would also be exceptionally bright compared to our moonlight, even dimly illuminated the moon during its nighttime. Even so, the Sun is 27 times dimmer than on Earth, and only a fifth of the size. Another spectacular phenomenon that occurs quite frequently are total solar eclipses viewed from the moon's perspective. The largest 4 moons of Jupiter, called the Galilean moons, are big enough to totally eclipse the Sun, and due to their orbital resonances, 3 can cast their shadow on Jupiter at the same time. Now, unbelievably, this is a real image captured by the Hubble Space Telescope, demonstrating this point. Already we are experiencing drastic differences in the skies of objects in our very own solar system. But let's take it one step further and go to the very last planet. Neptune is the very edge of deep space. At certain points of its year, it can be even further away from the Sun than Pluto, and the only thing found further out than Neptune are icy rocks. The Sun is only a 30th of the size in Neptune's sky, and Neptune receives roughly 1,000th of the sunlight Earth does. Our last visit for today will be on Triton, the largest of Neptune's moons. On the horizon, you will see its pale, thin atmosphere illuminated by the Sun. Neptune itself is 16 times bigger in the sky of Triton than how our moon would appear, but is 250 times dimmer. For us, the Sun is crucial for survival. On Triton, the temperature is minus 230 degrees centigrade, far too cold for us to survive. But to me, it's hugely interesting to know how different skies can look, even within our own solar system. I've only scratched the surface today of different views from different planets or moons, comets, and even asteroids. Each have their unique stories to tell, stories which we ourselves can discover. Look into the night sky on a clear night and you'll see thousands of stars spanning across your view. These stars are a beautiful reminder of the cosmos we live in. But curiously, when you look at the many different images released by space agencies of objects in space, the background looks mysteriously void of anything. Why is that? Surely with nothing in the way like an atmosphere, we should be able to see all the stars that would be in that view. In fact, even Apollo astronauts reported not being able to see any stars on the moon, where no atmosphere was in the way. So what's up with that? Well, this is all to do with how eyes and cameras work. When we look at a bright object, our iris shrinks in order to block out some of the light. This is what happened with the Apollo astronauts. Even though there was no atmosphere above them, the reflection of the sun's light from the moon's surface made their eyes adjust to as if it were day. One astronaut reported only being able to see some of the brightest stars when he was in the shadow of the lunar module, looking directly up with his protective visor raised. I imagine though, if astronauts ever land on the night side of the moon and have their eyes adjust to the near pitch black conditions, they would get a stunning view of the stars in our galaxy. When a camera on board a spacecraft images a planet, the shutter speed, or the amount of light a shutter allows into the camera before it closes again, is set for the equivalent of daytime levels. Because what we are usually looking at is the day side of the object. This shutter speed is too quick for background stars to be picked up. But every so often, we do want to image the night side of the object, which means we must increase the exposure time to allow more light into the camera. When this happens, suddenly the background becomes full of stars. This is a time-lapse of raw images taken by the Cassini spacecraft. As you can see, Cassini takes a lot of different images with different exposures. In some images there are no background stars visible, and in others there are. But this leads on to another interesting point about the images space agencies release to the public. You may have seen some of these stunning images of Saturn before, but you may not realize that this isn't one image, but it's rather a mosaic of several images stitched together. In such mosaics, you definitely won't see background stars, because the sections of black around the image won't have been added to the mosaic. Lots of spacecraft take images this way. The reason being, it can dramatically increase the resolution of an image and reduce the amount of data that has to be transmitted back. Bandwidth come in at quite a premium where data speed can be reduced to 2 kilobytes per second at the farthest distances. So there you go. Now you know why you don't tend to see stars in the background of space images.
A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape, a place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone. If you enjoy what we do, come join the Astrum community today.